Good morning. Today we are going to look at the economics of power supply. First of all, a few definitions. The average load is equal to the area under the daily load curve divided by 24 hours. The load factor is the average load divided by the maximum demand. Now, important terms and factors. The connected load, that is the sum of the continuous ratings of all the equipment connected to the supply system. Maximum demand, it is the greatest demand on the power station during a given period. Demand factor, the ratio of the maximum demand on the power station to its connected load. FD is your maximum demand divided by your connected load. Now the average load, the average of loads occurring on the power station in a given period can be in a day, month, or a year, and that is known as the average demand. Daily average load is a number of kilowatts generated per day divided by 24 hours. Monthly, same, divided by the hours in the month, and a yearly, divided by the number of hours in a year, which is 8,760. Then the load factor, that is the ratio of the average to the maximum demand during a given period. LF is the average load divided by the maximum demand. Now, if a plant is operated for a period of T hours, our load factor is the average demand load divided times by the time, divided by the maximum demand times the time. So that means it's the units generated in T hours divided by the maximum demand times T hours. The diversity factor is the sum of the individual maximum demands to the maximum demand on the power system. DF is the sum of the individual maximum demands divided by the maximum demand on the station. Plant capacity factor, that's the ratio of the actual energy produced to the maximum possible energy that could have been produced in a given period. So the plant capacity factor is the actual energy produced divided by the maximum energy that could have been produced, which is equal to the average demand divided by the plant capacity, which is equal to the annual kilowatt output divided by the plant capacity times 8,760. Plant use factor, that's the ratio of the kilowatt generated to the product of the plant capacity and the number of hours for which the plant was in operation. So therefore it is a station output in kilowatt hours times divided by the plant capacity times the hours of use. So that is the average load divided by the maximum demand, which is the maximum demand times the load factor, divided by the maximum demand times the load factor times 8,760. Now we look at the types of load that we can get. We have a domestic load, which is lights, fans, refrigerators, heaters, TVs, and so on. Then a commercial load is lighting for shops, fans, and electric applications in the restaurant. Industrial load is a load defined by industries depending on the type of industry. Municipal load, street lighting, water pump for water supply. Irrigation load, electric load for pump motors, and traction load, trains, tram cars, trolley buses, and so on. Now the cost of electrical energy can be divided in three parts. Fixed cost, independent of the maximum demand, and units generated. This is due to annual cost of central organization interest on capital cost of land, and salaries of high officials. Semi-fixed cost depends on the maximum demand, independent of units generated, the annual interest and depreciation on capital investments of building and equipment, taxes, salaries of management and clerical staff. Then we get to the running cost. That depends only on the number of units generated, annual cost of fuel, lubrication oil, maintenance, repairs, salaries of operating staff. Expression for the cost of electrical energy. We have a three-part form. Total annual cost of energy is equal to the fixed cost plus the semi-fixed plus the running cost. It is a constant plus proportional to maximum demand plus proportional to the kilowatt hours generated. So therefore the cost is in rands times A plus B kilowatt plus C kilowatt hours. A is the annual fixed cost. B times the kilowatt gives the annual semi-fixed cost. And C times the kilowatt hour gives the annual running cost. Now, if you look at the two-part form, that's the fixed sum per kilowatt of maximum demand plus the running charge per unit of energy. The cost is equal to rands times A kilowatt plus B kilowatt hours. A times kilowatt gives the annual cost of the first part, and B times the kilowatt hour gives the annual running cost. Now let's look at some methods of determining the depreciation. The straight line method is the total depreciation divided by the useful life, which is P minus S divided by N. P is your initial cost, S is the scrap value, N is the useful life in years. Then the diminishing value method, PA is equal to P times 1 minus S over P to the power 1 over N, where we have this same values for S and P. The sinking fund method, Q is equal to P minus S times R divided by 1 plus R to the power of N minus 1. Let's look at example 1. The equipment in a power station cost 1.56 million. The salaries due is 60,000 at the end of 25 years. Oh, sorry, the salvage value is 60,000 at the end of 25 years. Determine the depreciated value of the equipment at the end of 20 years using all three methods at a 5% compound interest. So there we have P is 1.56 times 10 to the power of 6. S is 60,000, N is 25. Now, again, according to the straight line method, that is P minus S divided by N. So that means it's 1.56 times 10 to the power of minus 6 minus 60,000 divided by 25 gives us 60,000. Now Q is P minus your annual depreciation factor times 20. And so that means it's 1.5 times 10 to the power of 6 minus 60,000 times 20. That gives us 360,000 Rand. Then the diminishing value, annual unit depreciation, X is equal to 1 minus S over P times to the power of 1 over N. That gives us 0.122. And therefore Q is equal to P 1 minus X to the power of 20. That gives us 1.5 times 10 to the power of 6 times 1 minus 0.122 to the power of 1 over 20. That gives us 115,119 Rand. Now using the sinking fund method, Q is equal to P minus S times R over 1 plus R to the power of N minus 1. Now, if you substitute all that, we get 31,428 Rand 70 cents. The sinking fund after 20 years, we substituted in there, Q is 1 plus R to the power of 20 minus 1 divided by 0.05. That gives us 1.039 million. So the value of the equipment after 20 years is 520,781. Right, example 2. The generating station has a maximum demand of 50,000 kilowatt. Compute the cost per unit generated from the following data. Capital cost, 95 million. Annual load factor, 40%. Annual cost of fuel and oil is 9 million. Total wages, taxes, wages, and salaries, 7.5 million. The interest and the depreciation is 12%. So the kilowatt hours per annum is the maximum demand times the load factor times the hours per annum. That's 50 times 10 to the power of 6 times 0.4 times 8,760. That gives us 1.175 times 10 to the power of 6 kilowatt. Interest and depreciation, 0.12 times 95 million gives us 11,400 times 10 to the power of 6. Then we look at the running charges. 9 times 10 to the power of 6 plus 7.5 times 10 to the power of 6, that gives us 16.5 million. So the cost per kilowatt hour is the total annual cost divided by the kilowatt hours generated. So the total cost then is 27.9 times 10 to the power of 6 divided by the number of kilowatt hours generated, 175 times 10 to the power of 6. That gives us a cost of 15 Rand and 92 cents. No, sorry, 15.92 cents. Example 3. A generating station has the following data. Installed capacity, 300 megawatt. Capacity factor, 50%. Annual load factor, 60%. Annual cost of fuel, etc. is 90 million. Capital cost is 1,000 million Rand. Per annum interest and depreciation is 10%. We must compute the maximum reserve capacity and the cost per kilowatt hour generated. Now, our capacity factor is the average demand divided by the installed capacity. And the load factor is the average demand divided by the maximum demand. And therefore, CF divided by LF, capacity factor divided by the load factor, gives us the maximum demand divided by the installed capacity. So the maximum demand is the installed capacity times the capacity factor divided by the load factor. That gives us 300 times 0.5 divided by 0.6, which is 250 megawatt. The reserve capacity is the total capacity minus the maximum demand. That means we have a 50 megawatt reserve capacity. The units generated per annum, maximum demand times the load factor times the hours. So that's 250 times 10 to the power of 3 times 0.6 times 8,760. That gives us 1,314 times 10 to the power of 6 kilowatt hours. So the fixed charges per annum is 1,000 million times 0.1 gives us 100 times 10 to the power of 6. Total cost per annum, fixed charges plus the per annum cost of the fuel. That gives us a total of 190 times 10 to the power of 6. The cost per kilowatt hour, total cost divided by the kilowatt per annum. That is 190 million divided by 1314. That gives us 14.46 cents per kilowatt hour. Example 4. The annual operating cost of a power station is given by A plus B kilowatt plus C kilowatt hours. Evaluate the values for A, B, and C for a 60 megawatt station operating a per unit per annual load factor of 50% from the following data. Capital cost of the building and equipment, 5 million. Per annum cost of fuel, oil, taxation, and wages, 900,000. Interest and depreciation is 10%. And the annual organization and interest on cost of the site, 500,000. So the kilowatt per annum is your maximum demand times the load factor times the hours. That gives us 262.8 times 10 to the power of 6 kilowatt hour. Now A is the annual fixed cost, which is 500,000. B is your annual semi-fixed cost, which is 500,000. 5 million times 0.1, which gives us 500,000. B times 60 times 10 to the power of 3 is 500,000. So therefore B comes down to 8 Rand and 34 cents. C is the annual running cost. That C times kilowatt hour is 900,000. And therefore C is equal to 0.343 cent. Example 5, hydroelectric plant cost 8,000 Rand per kilowatt hour of installed capacity. The annual charge is 5%. Of interest and depreciation is 2%. Operation and maintenance is 2%, and insurance, rent, etc. is 1.5%. Compute a suitable two-part tariff if the losses in the transmission and distribution is 12.5% and the diversity of load is 1.25. The maximum demand on the station is 80% of the capacity and your per annum load factor is 40%. And then what is the overall cost per kilowatt hour if the installed capacity is 100 megawatt? So your maximum demand is 100 times 10 to the power 8. That gives us 80 kilowatt. The average demand is your maximum demand times the load factor. That gives us 32 kilowatt. Capital cost of the plant is 100 times 3,000. That gives us 300 times 10 to the power of 3. The annual fixed charges due to 5% interest and depreciation is 300 times 10 to the power of 3 times 0.07, which is the sum of those two, which gives us 21 times 10 to the power of 3. The average of the maximum demand, the aggregate of maximum demand is 80 times 1.25, which gives us 100 kilowatt. The annual fixed charges is 21,000 divided by 100. That gives us 210 per kilowatt hour of maximum demand. The annual running charges due to the operations and maintenance is 2%, and insurance and rent, etc. is 1.5. So the running charges is 300,000 times 0.035, which gives us 10.5 thousand kilowatt per hour is the average demand times the hours, which is 32 times 8,760, which gives us 280.32 times 10 to the power of 3. And the unit reaching the customer is 280,320 kilowatt times 100 minus 12.5. That gives us 245.280 kilowatt. And the per annum running charges is 10,500 divided by 245.28 times 10 to the power of 3. That gives us 4.3 cents per kilowatt hour. So in a two-part tariff, we have 210 times the kilowatt plus 4.3 cent times kilowatt hour. So that gives us 21,000 plus 10,500. That gives us 31,500 rand. And the cost per kilowatt hour is then 31,500 divided by 242.28 times 10 to the power of 3. That gives us 13 cents. And this concludes our short introduction to the cost analysis. Thank you.